This is the very first lesson you must take when learning Wireshark protocol analysis. Ever been in a video call that suddenly turned into a choppy slideshow? Or seen your business system response time skyrocket for no reason? Speed tests say everything's fine, yet your users keep screaming, "It's laggy." Maybe you've tried capturing packets, drawing diagrams, running checks, but still couldn't find the real problem. Why does latency jump up and down? Why is bandwidth clearly enough, yet never fully used? Why does everything look normal, but the experience feels terrible? And here's the kicker. Maybe you troubleshoot one outage, document the cause, feel confident you'll fix the next one faster, only to find the next same-looking issue has a completely different root cause. All happy networks are alike. Each slow network is slow in its own way. So is slow really just about bandwidth? Not even close. The truth is, real network congestion is a system. It's not just not enough speed. It's a dynamic system, a feedback loop where senders react to loss, delay, and other signals, constantly adjusting their pace. This is the dance that controls every TCP backoff, every shrinking window, and every reallocation of link resources. This course will take you deep into the heart of transition performance through two models, the network path model and the network congestion model. The network path model simplifies any complex end-to-end path, no matter how many devices or links it has, into a single virtual link from TCP's perspective. At any moment, there's one bottleneck in each direction, controlling the flow, forming queues, and defining the connection's maximum throughput. The network congestion model takes it further, showing how the system behaves when data fills the pipe, depending on 8 key parameters, all of which you can observe or calculate using Wireshark. Sending rate, how much data the application pushes; delivery rate, how much the network actually delivers; bytes in flight, data in transit; round-trip time, RTT; buffer size, queuing delay; bandwidth delay product, and bottleneck bandwidth. Once you understand these models, the causes of slowness stop being mysterious. They become readable in the packets themselves. If you've ever opened Wireshark to analyze a transfer and thought, "What am I even looking at?" These models are the keys that unlock it. We'll cover it step by step in 8 parts. Part 1, overview of network congestion and bottlenecks. Part 2, hands-on setup for experiments. Part 3, the network path model. Part 4, the network congestion model. Part 5, real-world demos with Reno, the classic congestion control algorithm. Part 6, real-world demos with Cubic, the modern Linux default. Part 7, wrap-up, origins and evolution. Part 8, real-world applications. Due to the video length and other considerations, some chapters may need to be explained across multiple videos. The total number of our videos will exceed 8. Understanding these models is your gateway to advanced protocol analysis and performance troubleshooting. It's the foundation for mastering TCP congestion control, making sense of QoS, and for truly using Wireshark to solve real network problems. Don't stress if some concepts feel complex at first. Mark them, move on, and revisit after studying other supporting technologies. Like TCP congestion control algorithms, everything will click. And don't just watch, do the labs. Observe, verify, summarize. The learning is in the doing. This is hardcore technical stuff. So buckle up, stay focused, and let's dive into part 1 in next video.